welcome to the deep dive. So I want you to think about the last time you read a textbook, like maybe a university level physics or engineering text.
Oh, those massive heavy things we all had to lug around.
Yeah, exactly. But there is this, I don't know, a certain comfort in those books, right? They present the universe as this perfectly solved puzzle.
Bound by absolute mathematical laws.
Right. Gravity behaves this way, thermodynamics behaves that way. And in the incredibly complex world of nonlinear optics, there is this golden rule that dictates exactly how light is allowed to mix.
And it's a rule that's been around for over 50 years.
50 years. The established consensus has always been that if you take a perfectly symmetrical, just completely unorganized cloud of gas.
Something like the oxygen in the room you're sitting in right now.
Yeah, exactly. If you take that and you fire lasers into it, certain types of light mixing absolutely, categorically cannot happen.
It is considered a fundamental mathematical impossibility.
But today, we're looking at a paper that takes that foundational rule, sets it on an optical table, fires a pair of high-powered picosecond lasers at it, and just completely shatters it.
It really is one of those rare moments where you see the frontier of physics actively pushing back against the established doctrine.
I mean, it's mind-blowing.
It really is. The paper we're unpacking today is titled Non-Resonant Picosecond Three-Wave Mixing in the Gas Phase. And while the title sounds highly specialized,
very specialized,
the core finding is causing massive ripples. The researchers have definitively demonstrated that a phenomenon called some-frequency generation, which is a specific mechanism where two different colors of laser light fuse together to create a completely new color.
Right.
They proved it can and does occur in standard everyday gases like helium, nitrogen, and oxygen.
Which, if you follow classical optical theory, should be a total dead end. But I want to push back right away on why we're dedicating a deep dive to this.
Sure.
Because if I'm an engineer or someone working in applied sciences, I might look at some anomaly in a laser lab and think, okay, cool trick, but how does this affect my work?
Right. The so what factor.
Exactly. We need to be clear that this isn't just physicists finding a typo in a textbook.
Oh, it is far from it. This paper is basically handing the applied physics and engineering worlds a golden ticket.
A golden ticket to do what?
Well, by proving this phenomenon exists in standard gases, these researchers have unlocked an entirely new, completely non-intrusive method for measuring some of the most extreme, chaotic environments known to science.
We're talking about places where you can't just stick a thermometer.
Exactly. We're talking about the ability to precisely map the density of a gas inside a hypersonic scramjet engine while it's operating at Mach 5.
Wow.
We're talking about mapping the blistering exhaust of a rocket thruster or peering into the electrically chaotic superheated plasmas inside a fusion reactor. And they are doing it using nothing but light.
Freezing the action in a trillionth of a second. That is the hook for me. The ability to measure the unmeasurable. So, to get there, we are going to take you on a highly detailed journey today.
It's a fun one.
First, we have to unpack the forbidden physics, what the textbook rule actually says, and why the scientific community was so historically certain it was unbreakable.
Then we get to step inside the laser laboratory.
Yes. We'll look at the exact microscopic precision required to even attempt this experiment. Then, we're going to look at the data and watch the authors systematically play detective to hunt down and debunk decades of alternative theories that tried to explain this anomaly away.
And finally, we'll bring it back to the real world and explore how this new optical tool changes the game for aerospace and energy.
I think the most logical place to start is with the fundamental concept that makes this whole thing seemingly impossible. The rule revolves around a property called centrosymmetry.
Centrosymmetry, yeah.
Right. And for anyone who spends their time in crystallography or solid-state physics, centrosymmetry is a familiar concept. But in the context of gases, let's make sure we are all on the same page.
It's crucial for understanding the whole paper.
If you look at a highly ordered crystal, like quartz or a lithium niobate, something like that, the atomic lattice has a very specific rigid geometry. Depending on the crystal, there might be a definitive structural difference if you look up through the lattice versus down.
Exactly. They have an orientation.
But gases, by their very nature, are entirely isotropic. The molecules are in constant chaotic thermal motion.
Precisely. If you define a coordinate system within a volume of gas, and you pick any arbitrary point as your origin, the macroscopic physical properties you observe looking in the positive x direction will be mathematically identical to what you observe looking in the negative x direction.
Because it's just a random soup of molecules.
Exactly. That is a centrosymmetric medium. It possesses perfect inversion symmetry. Now, nonlinear optics is the study of what happens when you introduce incredibly intense electromagnetic fields, like those from a focused laser, into a material.
And at low intensities, light just passes through or reflects, like looking through a window.
Right. But at extreme intensities, the electric field of the light actually alters the optical properties of the material itself.
And this leads to the golden rule. The literature states that even-order nonlinear optical effects, specifically second-order effects, must completely vanish in any medium that possesses this centrosymmetry.
They have to vanish, mathematically.
But let's ground that math in something physical. When the electric field of a laser pulse hits a gas molecule, it interacts with the electron cloud, right? It pushes and pulls the charges, creating an electric dipole moment.
Yes. Think of the electric field of the light as a highly directional force. When it hits a molecule, it distorts the electron cloud, pulling the negative electron slightly away from the positive nucleus.
Kind of stretching it out.
Exactly, stretching it. This creates a tiny, localized polarization, a dipole. But remember, we are in a gas. It's completely chaotic and symmetrical.
Right, they're pointing in every possible direction.
Right. For every single molecule that happens to be oriented in a way that generates a positive dipole moment in a specific direction, statistical mechanics guarantees there is another molecule oriented the exact opposite way, generating an equal and opposite negative dipole moment.
So it's like a perfectly balanced tug of war on a macroscopic scale.
That is an excellent way to conceptualize it. Mathematically, the nonlinear susceptibility tensor, which is what dictates these effects, has to be invariant under spatial inversion.
Because flipping the coordinates flips the sign of the dipoles.
Right. So the only way the math holds up is if the entire second-order macroscopic susceptibility equals absolute zero. When you sum all those billions of microscopic dipoles across the laser's path, they perfectly cancel each other out.
A net polarization of zero.
Zero. And a net polarization of zero means no second-order optical effects can be generated.
Which brings us to some frequency generation, or SFG. This is the specific second-order effect the researchers are looking at today.
Yes, SFG.
At a foundational level, SFG is a three-wave mixing process. You take two distinct incident photons, let's say an infrared photon and a visible green photon, and they interact within the material to annihilate and spawn a third, entirely new photon.
And the frequency of this new photon is the exact mathematical sum of the two original photons.
Which is just so cool. And because photon energy is directly proportional to frequency, it perfectly satisfies the conservation of energy. If you add the energy of the infrared photon to the energy of the green photon, you get an ultraviolet photon.
It is a brilliant, elegant quantum interaction. But, as we just established, it is a second-order nonlinear process.
Uh-oh.
Yeah. Therefore, according to the inviolable rule of centrosymmetry, the macroscopic dipole cancellation means the infrared and green light should just pass right through the gas.
Nothing should happen.
Exactly. The gas cannot mediate the combining of those photons. The textbook says the signal must be zero.
But wait. I know from looking at the history of nonlinear optics that this isn't the first time someone claimed to see a signal where they shouldn't. If we go back to the literature from the 1970s and 1980s, you have researchers like Donald Bethune reporting anomalous light mixing in atomic vapors.
That's true, yeah.
So if the rule is absolute, how were they getting published 50 years ago?
That is a crucial piece of historical context. Bethune and his contemporaries weren't actually breaking the centrosymmetry rule. They were exploiting highly specific quantum loopholes.
Loopholes? Like what?
Well, they were working with alkaline metal vapors, things like sodium or rubidium that actually have to be heated in ovens to vaporize. And they utilized two very strict conditions. First, their process was entirely resonant.
Resonant, meaning they weren't just blasting the vapor with any random laser. They had to tune their incident lasers to match the exact atomic transition frequencies of the sodium atoms.
Exactly. They were matching the natural resonance of the electrons. The energy of the photons had to precisely match the energy gap between specific quantum states in the atom.
And what does that do?
When you do that, you massively artificially inflate the nonlinear response.
Right.
But even with resonance, the dipole cancellation rule still applies.
Right, because it's still a gas.
Exactly. So the second part of their loophole was relying on higher order multipole interactions, specifically quadrupole effects.
Okay, let me stop you there, because the leap from a dipole to a quadrupole usually loses people. A dipole is a simple separation of charge, a positive end and a negative end. What makes a quadrupole different in a way that lets it bypass this rule?
A quadrupole is a more complex distribution of charge. Instead of just a single positive and negative pole, imagine an arrangement of 4 alternating charges.
Like a square with alternating plus and minus corners.
Basically, yes.
Right.
And the mathematical symmetry of a quadrupole is fundamentally different from a dipole. While a dipole moment changes sign under spatial inversion, which is why it cancels out in a gas, a quadrupole moment does not change sign under spatial inversion.
Ah, so the quadrupole mathematically survives the chaos of the gas.
Precisely. By using perfectly tuned resonant lasers, Bethune and others were able to excite these very weak, highly specific quadrupole transitions.
But it sounds incredibly difficult to do.
Oh, it was. To even detect them, they had to cross their laser beams at very specific angles and use complex polarization setups. It proved that if you cheat the system hard enough, you can find a tiny loophole.
But it confirmed the overarching rule.
Exactly. It confirmed that simple off-resonant dipole mixing in a gas is impossible.
Which frames exactly why this new paper is such a massive disruption. The researchers here didn't use an oven full of heated sodium vapor.
Right.
They didn't tune their lasers to match the precise quantum transitions of the atoms, and they didn't rely on complex crossing angles to hunt for weak quadrupole signals.
They did none of that.
They took ordinary room temperature gases, helium, argon, oxygen, nitrogen. They fired brute force off-resonant laser pulses at them. And despite the perfect centrosymmetry, despite the complete lack of resonance, they generated a massive, undeniable some-frequency generation signal.
They mixed the light.
It creates a fascinating tension. If the textbook says it's impossible and the historical precedents all relied on incredibly specific resonant quadrupole loopholes, how on earth did they do this with ordinary gas and off-resonant light?
To answer that, we have to look at the physical setup. The precision required to execute an experiment like this without drowning in false positives is just staggering.
Let's transition into the lab then. I think it's easy to read a physics paper and abstract the experiment into a clean, simple diagram with a few lines and boxes.
Right, it looks so simple on paper.
But the physical reality of a modern nonlinear optics table is anything but simple. I want to try to visualize this for you. We are looking at a massive vibration-isolated optical table. It's essentially a heavy metal slab floating on pneumatic legs so that even a truck driving by outside doesn't ruin the alignment.
And bolted to that table is an absolute maze of highly specialized optics.
A maze of mirrors and lenses.
Exactly. And the engine of this entire setup is an ND.YAG laser. ND.YAG stands for neodymium-doped yttrium aluminum garnet. It's a solid-state laser where the active gain medium is a synthetic crystal.
And we should clarify, this isn't a continuous wave laser. It's not a laser pointer that just stays on. It's a pulsed system. The paper notes it fires at a repetition rate of 50 hertz, so 50 pulses a second.
Right.
But the crucial metric here is the pulse duration. Each individual burst of light lasts for exactly 30 picoseconds.
That pulse duration is everything. A picosecond is 1/trillionth of a second. To ground that in physical reality, light is the fastest entity in the universe, traveling at roughly 300,000 kilometers per second.
Unimaginably fast.
But in a window of just 30 picoseconds, a pulse of light only travels about 9 millimeters.
That is wild. So we aren't talking about a continuous beam. We are talking about literal bullets of light, less than a centimeter long, flying across the optical table.
Bullets of light is a perfect way to put it. Now, the primary beam coming out of that ND.YAG laser is infrared with a wavelength of 1064 nanometers.
Which means it's completely invisible to the human eye.
Completely invisible. The first operation they perform is passing a portion of that primary beam through a frequency doubling crystal. This is a standard nonlinear process called second harmonic generation, and it converts some of that infrared light into a secondary beam of bright green light at 532 nanometers.
Okay, so now they have their two distinct inputs, the 1064 nanometer infrared beam and the 532 nanometer green beam.
Right.
But looking at the experimental schematic in the paper, they don't just immediately point them at the gas chamber. They hit an equilateral dispersion prism, which physically splits the two colors apart, sending them down completely separate paths on the table.
Yes, they do.
If the entire goal of this experiment is to smash these two colors together in the gas, why are they actively splitting them apart on the table first? It seems like you're just asking for alignment headaches.
It absolutely creates alignment headaches, but it's a necessary evil for total experimental control. By separating the two colors into distinct beam paths, the researchers can independently manipulate the properties of each beam.
Ah, I see.
They insert specific half-wave plates and thin film polarizers into each path. This allows them to independently dial the power intensity of the infrared beam without affecting the green beam, and vice versa.
Which is going to be incredibly important for the data later.
Exactly. And more importantly, it gives them total control over the polarization state of each beam. They can rotate the electric field of the infrared light to oscillate vertically while leaving the green light horizontal, or make them both parallel. You cannot do that if the beams are traveling on top of each other.
That makes total sense. You need granular control over the variables, but that means you have to eventually recombine them. And this is where that 30 picosecond pulse duration becomes a massive logistical nightmare, right?
Oh, it really does. They use a dichroic mirror, which reflects the green light but transmits the infrared light, to merge the two beam paths back into a single collinear trajectory.
But remember, these are 9 mm long bullets of light.
Right. If the physical path length of the green beam on the table is even slightly longer than the path length of the infrared beam, the green bullet will arrive at the gas chamber fractions of a nanosecond too late.
And the two pulses will literally physically miss each other in time.
Exactly. They'll miss each other and no mixing can occur.
I can only imagine the frustration of the grad students tasked with aligning this. How do they synchronize them?
They implement an optical delay line in one of the beam paths. It's essentially a pair of mirrors mounted on a highly precise linear translation stage.
Yeah.
By turning micrometer screws or using piezoelectric actuators, they can physically lengthen or shorten one of the paths by fractions of a millimeter until the arrival time of both pulses perfectly overlaps.
So they have perfectly synchronized, precisely polarized bullets of infrared and green light traveling together.
Ready for the gas.
The final step before the gas is the focusing lens. They pass these merged beams through a lens that pinches them down to an incredibly tight focal spot, just 40 micrometers in diameter.
We're talking less than the width of a human hair.
And this focal point is positioned dead center inside a custom-built stainless steel pressure chamber.
The chamber is highly controlled. It's connected to a vacuum system that can evacuate the chamber down to a high vacuum, removing any atmospheric contaminants.
So it's completely empty.
Then they backfill it with their test gases. They used ultra-high purity grades of helium, argon, krypton, oxygen, and nitrogen. And they monitor the internal pressure with capacitance manometers, which are highly accurate pressure sensors that operate independently of the gas composition.
Now, here is where my skepticism flares up. You are taking a laser pulse that is already incredibly powerful, and you are focusing it down to a 40 micrometer spot. The power density at that focal point must be astronomical.
It is extreme.
The paper lists the intensity at several trillion watts per square centimeter.
Trillions, yeah.
If I am a reviewer reading this paper, my immediate thought is that you aren't discovering new physics. You are just accidentally creating a plasma spark in the gas, and that spark is emitting broadband light that looks like a signal.
That is the number one critique. Laser-induced breakdown is the most critical false positive you have to avoid in gas-phase nonlinear optics.
Because what happens exactly?
When an electric field reaches those intensities, it can overcome the binding energy of the electrons, ripping them completely away from the gas molecules through multiphoton ionization and avalanche ionization.
Basically tearing the atoms apart.
Yes. This creates a microplasma. A plasma is a chaotic soup of ions and electrons, and it emits an intense continuum of light across the entire spectrum. If that happens, your signal is contaminated. It's basically a tiny lightning bolt.
So how do they prove they are measuring pristine gas and not a tiny lightning bolt?
They approach it with extreme rigor. The threshold for laser-induced breakdown is a known quantity for these gases at specific pressures and laser wavelengths. The researchers deliberately mapped out this threshold for their specific focal geometry.
So they knew exactly where the edge was.
Exactly. During the actual data collection, they strictly maintained the combined intensity of their laser pulses well below this breakdown threshold limit.
But how can they be sure it didn't start?
They confirmed this both through empirical optical observation, literally looking for the telltale flash of a spark, and by monitoring for any free electron current in the chamber. They essentially proved mathematically and physically that their energy levels were insufficient to ignite a plasma.
Okay, so plasma is ruled out. But what about the chamber itself? The light has to enter and exit through solid glass windows.
Right, fused silica windows.
And solid glass is not a chaotic gas. It is a dense, structured material that is well known to generate its own nonlinear optical effects, like third harmonic generation. Couldn't the windows be generating a signal that they mistake for the gas?
Another excellent point. To mitigate window artifacts, they implemented two safeguards. First, right before the entrance window, they placed a 450 nanometer long pass filter.
And what does that do?
This completely blocks any stray ultraviolet light that might have been accidentally generated by the lenses or crystals earlier on the optical table. Only the pure infrared and green beams enter the chamber.
So nothing sneaky gets in.
Wait.
And the second safeguard?
Geometry. When the merged beams pass through the fused silica entrance window, they haven't reached the focal point yet.
Ah, they're still wide.
Exactly. The beam diameter at the window is relatively wide, several millimeters across. Because nonlinear effects scale exponentially with light intensity, the intensity at the window is far too low to generate a significant signal.
That makes perfect sense.
The extreme trillion watt per square centimeter intensities only occur at that microscopic 40 micrometer focal point, which is suspended in the dead center of the gas, far away from any solid surfaces.
That is bulletproof experimental design. They've isolated the variables, prevented breakdown, and eliminated boundary effects. So they flip the switch. The pulses smash together in the center of the perfectly symmetrical gas. What actually hits the detector on the far side of the chamber?
Emerging from the exit window, completely invisible to the human eye, is a beam of 355 nanometer ultraviolet light.
355 nanometers.
Yes. It is captured by a highly sensitive photomultiplier tube, completely isolated by interference filters so that only that specific wavelength is detected.
And 355 nanometers is the smoking gun. Because if you do the math, taking the inverse of the 1064 nanometer wavelength and adding it to the inverse of the 532 nanometer wavelength, it equals exactly the inverse of 355 nanometers.
It's just perfectly elegant.
It is the perfect mathematical sum of the two input frequencies.
It is. The light undeniably mixed. But seeing a 355 nanometer signal isn't enough on its own.
Because it could be a fluke.
Right. The researchers had to prove definitively that this ultraviolet light was the direct result of a three-wave mixing process between the two specific input beams and not some bizarre higher-order artifact involving just one of the beams.
Right, and to prove that, they ran a power scaling test. If we look at the data in figure 2A of the paper, we can see exactly how they interrogated the signal.
It's a very clever test.
They took the green beam and held its power perfectly constant. Then, using those wave plates we talked about earlier, they slowly ramped up the energy of the infrared beam. And as the infrared power increased, the intensity of the ultraviolet signal increased in a perfectly linear lockstep fashion.
Then they ran the reciprocal test. They held the infrared beam steady and ramped up the green beam. Again, the ultraviolet signal scaled perfectly linearly.
And why is that linear relationship so important?
This is the definitive proof of some frequency generation. The theoretical macroscopic intensity of an SFG signal is governed by an equation where the output intensity is directly proportional to the product of the two input intensities.
So I dot over n times I tol 2.
Exactly. The fact that the output responded linearly to independent changes in both IDOLA and IDOLA22 proves categorically that one photon from the infrared beam is fusing with one photon from the green beam.
And let's be clear about the magnitude of what they found. When I first read the abstract, I assumed they were finding some microscopic edge case, like a signal so weak it was barely above the background noise of the detector.
A lot of people probably thought that.
But the authors compared the strength of this forbidden SFG signal to a well-known permitted nonlinear process called third harmonic generation, or THG.
Yes, and the comparison is staggering. In identical gas conditions, the sum frequency generation signal was approximately 4 orders of magnitude stronger than the third harmonic generation signal.
4 orders of magnitude, that's 10,000 times stronger.
Exactly. It completely upends the expectation. A supposedly forbidden process is dominating a permitted process by a factor of 10,000.
That's insane.
This isn't a negligible error rate in the symmetry. This is a highly efficient, robust physical mechanism.
Which naturally leads to the next question. How does the gas itself affect this massive signal? The researchers took their pressure chamber and started varying the density of the gas inside.
Pumping it up.
Right. They started at a near vacuum, around 20 torr, and steadily pumped more gas in, crossing normal atmospheric pressure and going all the way up to 1100 torr.
And this is where the data gets incredibly exciting for the engineering community. As they increase the pressure packing more and more gas molecules into that tiny 40 micrometer focal volume, the strength of the ultraviolet signal scaled quadratically.
Okay, I want to spend a minute on quadratic scaling, because it is the linchpin for why this is so useful later on. If the signal scaled linearly, It would mean that if you doubled the gas pressure, the signal would simply double. It's a one-to-one relationship.
Correct. But quadratic scaling, mathematically represented as a null squared, where null is the number density of the gas molecules, is entirely different.
How so?
If you double the gas density, the signal doesn't double. It increases by a factor of 4. If you triple the gas density, the signal is 9 times stronger. If you increase the density by a factor of 10, your signal jumps by a factor of 100.
It's an exponential curve. This means the process is highly sensitive to the exact concentration of molecules.
Extremely sensitive.
But the researchers didn't stop at just one gas. They wanted to see if the chemical identity of the centrosymmetric gas mattered. So they ran this pressure scaling test across all 5 gases: krypton, argon, oxygen, nitrogen, and helium.
And a very distinct, repeatable hierarchy emerged from the data. At any given pressure, krypton was the undisputed champion, producing a massive signal.
Krypton was at the top.
Right. Argon and oxygen were grouped together in the middle, producing significantly less signal than krypton, but still robust. Nitrogen was further down, and helium produced the absolute weakest signal of the group.
I find this fascinating. They are all centrosymmetric gases. Krypton and helium are both noble gases, meaning they are chemically inert and incredibly stable. Why does krypton crush helium so thoroughly in this optical mixing process?
It comes down to quantum mechanics and a property called nonlinear hyperpolarizability.
Hyperpolarizability.
Yes. Earlier, we talked about how the electric field of the laser distorts the electron cloud of the atom, creating a dipole. Hyperpolarizability is simply a quantitative measure of how susceptible a given atom's electron cloud is to being stretched and warped by an external field.
Okay, so why are they so different?
Think about the atomic structure. Helium is atomic number 2. It has exactly 2 electrons, and they reside in the 1's orbital, which is the lowest possible energy state, sitting incredibly close to the 2 protons in the nucleus.
Right, they're huddled right up against the center.
Because they are so close, and because there are no other electrons between them and the nucleus, they feel the absolute, unshielded electrostatic pull of those protons. They are locked down tight. If the laser's electric field tries to pull on them, they barely budge.
Right, it's an incredibly rigid, compact atom.
Now look at krypton. Krypton is atomic number 36. It's massive compared to helium. Its outermost electrons, the valence electrons that interact with light, are all the way out in the 4p orbital.
So they are far away from the center.
Not only are they physically much farther away from the nucleus, but they're also shielded from the nucleus's positive charge by 28 inner shell electrons. The effective nuclear charge holding those outermost electrons in place is relatively weak.
So they are loosely bound. When that trillion-watt laser pulse hits a krypton atom, that massive, sprawling electron cloud just sloshes and distorts violently.
Exactly. Krypton's electron cloud is highly polarizable, and the experimental data perfectly reflects this quantum reality. If you look at Table 1 in the paper, which lists the known second hyperpolarizability values for these gases, krypton is rated at roughly 77.
Okay.
Argon is 32. Helium is an abysmal 1.0.
Wow, 77 down to 1.
The hierarchy of the some-frequency generation signal strength aligns flawlessly with the hyperpolarizability of the atoms. The more easily the gas distorts, the stronger the forbidden signal.
It is beautiful when the macro-level data perfectly aligns with the quantum theory like that. But we still have a massive problem, the elephant in the room.
Yes, we do.
The data is pristine, the quadratic scaling is confirmed, the hyperpolarizability lines up. But why is it happening at all? How is this off-resonant light bypassing the fundamental rule of centrosymmetry?
And this brings us to what I consider the most intellectually rigorous part of the paper. The authors knew they had observed a massive anomaly, and they knew the historical physics establishment wouldn't just rewrite the textbooks based on one clean data set.
Because reviewers would tear it apart.
Reviewers would immediately attempt to explain the signal away using established historical loopholes.
So the authors play detective. They proactively identify the legacy theories that could potentially explain the anomaly, and they devise specific targeted experiments to test and ultimately falsify those theories.
It's the scientific method at its absolute best.
You don't just prove what you think is right. You actively try to destroy your own findings with alternative explanations.
Exactly. Let's look at their suspect list. Suspect number 1 is the quadrupolar effect. We discussed this earlier with Bethune's work in the 70s. The established optics community could look at this data and argue, you aren't breaking the centrosymmetry rule, you are just exciting higher-order quadrupole moments in the gas. It's a known, albeit weak, mechanism.
So how do you disprove that? You look at the mathematical constraints of quadrupole theory. The established theory dictates that quadrupole-mediated some-frequency generation is highly dependent on the polarization vectors of the incident lasers.
Right. Specifically, it predicts that the mixing can only occur efficiently if the two input lasers are cross-polarized.
Meaning the electric field of the infrared beam must be oscillating vertically, while the electric field of the green beam oscillates horizontally. If the beams are collinear, meaning their polarizations are parallel, the quadrupole interaction mathematically drops to near zero.
So the authors run a polarization test. They use their independent waveplates on the optical table to precisely align the polarizations. First, they configure both the primary infrared beam and the secondary green beam to be collinearly polarized in the vertical direction.
According to the legacy quadrupole theory, this should result in no signal.
But when they fire the lasers, they record a massive ultraviolet signal. And more importantly, through polarization analysis of the output, they find that the generated ultraviolet light is also perfectly vertically polarized.
They then rotate the waveplates 90 degrees, setting both input beams to be horizontally polarized, and again, a massive signal emerges, perfectly horizontally polarized.
This simple, elegant test completely destroys the quadrupolar hypothesis. The fact that the strongest some-frequency signals were generated under collinear polarization conditions is fundamentally incompatible with the theoretical frameworks and historical observations of quadrupole-induced mixing.
So suspect number 1 is definitively eliminated.
Gone.
Okay, so if it's not quadrupoles, we move to suspect number 2. And this suspect is much more insidious. It's based on a theory proposed in the 1980s by a researcher named Miyazaki, and it revolves around the concept of a static electric field induced by charge separation.
Miyazaki's theory is actually a brilliant piece of deductive reasoning. It acknowledges the centrosymmetry rule, but proposes a mechanism where the laser itself temporarily destroys the symmetry of the gas.
How does it do that?
The theory posits that even if you keep the macroscopic laser intensity below the absolute breakdown threshold for a plasma spark, the microscopic intensity at the absolute center of the focal spot is still high enough to cause a tiny amount of multiphoton ionization.
Let's unpack multiphoton ionization because it's distinct from how we usually think about photoelectric effects. Normally, to eject an electron from an atom, you need a single photon with a high amount of energy, like an ultraviolet or X-ray photon.
Right.
An infrared photon, like the 1064 nanometer beam they were using, simply doesn't have enough energy to overcome the ionization potential of an argon or krypton atom.
That's true in linear optics. But in the extreme nonlinear regime, if the photon density is high enough, an atom can absorb multiple low-energy infrared photons simultaneously. Their combined energy bridges the gap, allowing the atom to eject an electron.
So Miyazaki argues that this intense laser pulse is ripping a small number of electrons free.
Yes, and here is where the charge separation happens. When an electron is ejected, you are left with two particles: a negatively charged free electron and a positively charged heavy ion.
Okay.
Because electrons are incredibly light, the intense electromagnetic fields of the laser accelerates them radially outward from the focal center incredibly fast. The positive ions, being thousands of times more massive, essentially stay put.
This creates a microscopic, localized separation of charge, a clump of positive ions in the center, surrounded by a diffuse cloud of negative electrons.
And anytime you have a separation of positive and negative charges, you generate a static electric field between them.
Right.
Miyazaki hypothesized that this laser-induced microscopic static electric field acts upon the surrounding non-ionized gas molecules. It forcefully aligns them, creating a preferred direction, essentially establishing a temporary up and down within the focal volume.
And that transient static field breaks the centrosymmetry of the gas, permitting the some-frequency generation to occur.
Exactly.
I have to admit, if I'm reading the literature, that theory sounds incredibly plausible. It respects the foundational rules, but finds a dynamic laser-induced mechanism to bypass them. It's a great theory.
It really is.
But our researchers weren't buying it, so they subjected suspect number 2 to an absolute brutal interrogation.
To test Miyazaki's theory, they realized they didn't need to measure the microscopic internal electric field. They just needed to overwhelm it.
Like overpower it completely.
Yeah, right. If the entire some-frequency process relies on a delicate, transient, static electric field to break the gas's symmetry, then introducing a massive, permanent external electric field from outside the chamber should severely interfere with the process and drastically alter the signal output.
So they modify their pressure chamber, they install high voltage electrodes directly across the focal region of the gas, and they apply an external DC electric field of up to 20 kilovolts per centimeter.
20,000 volts per centimeter.
So we need to pause and appreciate how terrifyingly high that voltage is. For context, the dielectric breakdown of normal air at standard pressure, the point where air literally rips apart and arcs like lightning or a spark from a doorknob, happens at roughly 30 kilovolts per centimeter.
They were pushing this gas to the absolute brink of catastrophic electrical breakdown.
They were bombarding this perfectly symmetrical gas with a massive sledgehammer of an electric field.
The expectation under Miyazaki's theory is clear. This massive external field should dominate any microscopic charge separation effects. It should forcefully align the dipoles of the gas, permanently breaking the centrosymmetry, and thereby wildly enhancing or altering the some frequency signal.
So they turn on the 20,000 volt field, they fire the lasers, they check the detector, and what happens?
Absolutely nothing.
Nothing. The signal output is identical to when the external field was turned off.
They swept the voltage from 0 all the way up to 20 kilovolts per centimeter. The intensity of the 355 nanometer ultraviolet signal did not fluctuate, it did not enhance, it did not degrade.
Wow.
The some frequency generation process proved to be completely 100% independent of external static electric fields.
Which is the absolute nail in the coffin for Miyazaki's theory. If the mixing relied on a weak laser-induced static field, hitting it with 20,000 volts per centimeter would have completely overwritten the process.
It would have completely changed the signal.
Yeah.
Suspect number 2 is dead.
It is a phenomenal piece of experimental falsification. They eliminated quadrupoles and they eliminated static charge separation. The classical textbook rule is shattered, and the legacy workarounds are proven inapplicable.
Which leaves us in an interesting place. The authors are incredibly transparent in the paper. They have definitively proven what the mechanism isn't, but they stop short of definitively declaring what the mechanism is. They leave it as a lingering frontier mystery.
They do offer one hypothesis, pointing to older theoretical work by Freeman and colleagues from 1981 regarding induced anisotropy.
Yes. The concept here is that a focused laser beam is not a perfectly uniform cylinder of light. It has a Gaussian spatial profile. It is incredibly intense in the absolute dead center, and the intensity falls off rapidly as you move toward the radial edges of the beam.
So there's a massive gradient of light intensity across a microscopic distance.
Precisely. Freeman hypothesized that this extreme spatial variation, the steep gradient of the electromagnetic field, might be inducing an anisotropic state in the gas.
Wait, can you clarify what that means for the gas?
Essentially, the shape of the laser pulse itself is violently warping the density or the isotropic properties of the electron clouds strictly along the gradient of the beam. This creates a highly localized, transient asymmetry that allows the waves to mix.
It's a fascinating theory. And it leaves the physics community with a massive, exciting problem to solve. They know the phenomenon is real. They've built a bulletproof experimental setup that anyone can replicate. They've cleared away the incorrect historical assumptions, but the fundamental quantum mechanics of the interaction are still up for debate.
Exactly.
But, and this is where we pivot to the engineering implications. I want to argue that for a massive segment of the scientific community, the exact quantum mechanism doesn't actually matter right now.
It really doesn't.
They don't care why it works. They only care that it works and how predictably it scales. Because this broken rule is arguably the most important diagnostic breakthrough for extreme environments in a decade.
I completely agree. The theoretical physicists will argue about induced anisotropy for years, but the engineers are taking this data and running with it today. We need to connect this high-level laser physics back to the real world. Why does this matter? It all boils down to the science of measurement in places where physical measurement is impossible.
Let's revisit that quadratic scaling data we deked out over earlier. The fact that the signal strength scales perfectly with the square of the gas density, because the signal flawlessly tracks the density of the gas molecules, and because the process happens instantly during a 30 picosecond laser pulse, engineers have effectively been handed a brand new God-tier diagnostic tool.
Some researchers are calling it the picosecond ruler.
The picosecond ruler. To understand why this is so revolutionary, we need to look at the limitations of current aerospace engineering. Let's take the development of hypersonic scramjet engines.
Right, scramjets.
A scramjet, a supersonic combustion ramjet, is an engine designed to propel vehicles at Mach 5, Mach 10, or even faster. Unlike a traditional jet engine that uses spinning turbine blades to compress incoming air, A scramjet relies entirely on the forward speed of the vehicle to forcibly ram air into the combustion chamber.
And the physics inside that chamber are a nightmare. The air is blasting through the engine at supersonic speeds. You have to inject fuel into that supersonic flow, mix it perfectly, and ignite it in milliseconds before it gets blown out the back. Aerospace engineers often compare it to trying to keep a match lit in a Category 5 hurricane.
So the entire design of a scramjet relies on understanding the exact fluid dynamics inside that chamber. You need to know the precise density gradients of the air, where the shock waves are forming, and how the mixing is occurring.
Because if your density calculations are off by a fraction, the engine unstarts, which is a catastrophic failure where the supersonic flow breaks down and the engine violently chokes.
So you need data, but how do you get it? You can't just drill a hole in the side of a Mach 5 engine and stick a physical pressure probe inside.
Exactly. Sticking a physical sensor into a hypersonic flow introduces two fatal problems. First, the thermal and kinetic friction of air moving at Mach 5 will melt or shear off almost any physical probe you insert.
It would just disintegrate.
Second, even if the probe survives, the physical object itself acts as an obstruction. When supersonic air hits a physical probe, it creates a massive bow shock, a shock wave, that radically alters the local pressure, density, and temperature of the gas around it.
By trying to measure the flow, you completely destroy the flow you are trying to measure. The Heisenberg uncertainty principle applied to macrofluid dynamics.
Which is why the aerospace industry has heavily invested in non-intrusive optical diagnostics. You put a sapphire window on the side of the test engine and you shoot lasers through the flow. Because photons have zero rest mass, they pass through the supersonic air without creating shock waves or disrupting the fluid dynamics.
But traditional optical techniques have severe limitations, don't they? Some require seeding the gas flow with toxic or reactive tracer chemicals like nitric oxide.
Yes, and others rely on resonant laser techniques, which means you have to tune your lasers to the exact highly specific absorption frequency of the gas, which can shift wildly depending on the extreme temperatures inside the engine.
And this is where the off-resonant some-frequency generation technique changes everything. Because it operates off resonance, you don't have to perfectly tune your lasers. You can use standard, robust, commercial N.YAG lasers.
And because it doesn't require seeding, you can measure the raw, native gases, the oxygen and nitrogen, already present in the airflow.
And most importantly, because you are using 30 picosecond laser pulses, you are taking a snapshot of the engine in a trillionth of a second. At Mach 5, a gas molecule moves about 1.7 millimeters in a single microsecond. But in a picosecond, it barely moves the width of an atom.
You are completely freezing the chaotic supersonic motion. You fire the two invisible beams in, the beams cross at a microscopic 40 micrometer point, and the exact intensity of the ultraviolet light that flashes out tells you the precise, absolute density of the gas at that specific microscopic coordinate.
In real time, without disturbing a single molecule.
It is an unparalleled capability for mapping high-speed aerodynamics. But honestly, as massive as the implications are for hypersonic flight, the true superpower of this technique, the thing that makes it entirely unique, is what we discovered during the debunking of Miyazaki's static electric field theory.
The 20 kilovolt interrogation, the plasma advantage.
Yes. When they proved that the some-frequency generation signal is completely immune to external electric fields, they inadvertently solved one of the biggest measurement crises in modern physics: measuring plasmas.
Let's talk about plasmas, because they are everywhere in high-end technology. A plasma is often called the fourth state of matter. If you take a gas and heat it to extreme temperatures, or subject it to extreme electromagnetic fields, the electrons are violently stripped away from the atomic nuclei.
You are left with a chaotic, swirling, highly reactive soup of negatively charged free electrons and positively charged heavy ions.
Plasmas are the core of experimental fusion energy. Inside a tokamak reactor, we are trying to recreate the power of the sun by compressing a plasma of hydrogen isotopes using massive magnetic fields.
And plasmas are also the backbone of the semiconductor industry. To etch the microscopic, nanometer-scale transistors onto a silicon wafer, manufacturers use highly corrosive, low-pressure plasmas.
In both of those cases, fusion and semiconductor fabrication, understanding the exact density and behavior of the plasma is the difference between success and catastrophic failure. But measuring a plasma is notoriously, brutally difficult.
And it goes back to charge separation. Because a plasma is literally made of trillions of freely moving electrical charges, it generates its own wild, unpredictable, highly localized electric and magnetic fields. It is an environment of supreme electrical noise.
If you tried to stick a traditional electrical probe, like a Langmuir probe, into a dense plasma, the probe's own electrical potential interacts with the plasma, changing a local density, and the extreme heat often destroys the probe.
So again, you turn to lasers, you try to use optical diagnostics.
But many traditional nonlinear optical techniques are highly sensitive to electric fields. If you try to measure a plasma using a technique that relies on Stark effects or other field-sensitive mechanisms, the chaotic, screaming electrical noise of the plasma completely overwhelms the subtle optical signal you are trying to read.
It's like trying to listen to a whisper at a heavy metal concert. The signal-to-noise ratio is abysmal.
But this new SFG technique doesn't care about the electric field. The authors mathematically and physically proved it. Bombarding the gas with 20,000 volts per centimeter did absolutely nothing to alter the signal.
Which means engineers can take this off-resonant picosecond laser setup, point it directly into the roaring, electrically chaotic heart of a tokamak fusion reactor, or into a semiconductor etching chamber, and fire.
The intense electric fields of the plasma will have zero effect on the three-wave mixing process.
The some-frequency generation signal will cut straight through the electrical noise, completely unbothered, and deliver an exact, perfectly scaled measurement of the molecular density inside that microscopic focal spot. It is an absolute game-changer for plasma physics.
It's an incredible narrative arc. You start with a rigid mathematical rule that says a specific interaction in a perfectly symmetrical gas is fundamentally impossible. Then, you step into a laboratory and watch researchers meticulously build an optical gauntlet using perfectly timed 30 picosecond bullets of infrared and green light to undeniably prove that the forbidden interaction actually happens, generating a massive ultraviolet signal.
We saw them systematically dismantle decades of established theories, using elegant polarization alignments to kill the quadrupole hypothesis and unleashing a terrifying 20,000-volt electric field to disprove the static charge separation theory. They cleared the slate, leaving us with a beautiful new quantum mystery regarding induced anisotropy.
And finally, we saw how that broken rule transitions from a physics curiosity into a vital engineering tool. By proving the signal scales quadratically with density and is completely immune to electrical noise, they have handed aerospace engineers and fusion researchers a flawless, non-intrusive picosecond ruler capable of peering into Mach 5 scramjets and superheated tokamaks. It perfectly illustrates how pushing the absolute boundaries of foundational physics directly catalyzes massive leaps in applied technology.
It really does.
Before we finish, I want to leave you with a final thought to mull over. Something that takes this highly controlled laboratory discovery and applies it to the wild, uncontrolled universe.
Oh, I like where this is going.
We just spent an hour discussing how researchers proved that our fundamental assumptions about how intense light interacts with basic everyday gases were incomplete for 50 years. And they proved it using highly engineered lasers in a pristine vacuum chamber.
Right, very controlled.
But think about the extreme environments that occur naturally in our universe. If this impossible light mixing can be forced to happen with picosecond bursts of electromagnetic energy in a lab, what kind of forbidden nonlinear optical phenomena might be occurring naturally right now?
That's a great question.
Think about a massive lightning strike, an environment characterized by immense instantaneous optical intensity, massive temperature gradients, and chaotic electrical power ripping through the symmetric nitrogen and oxygen of our atmosphere. Or consider the upper atmosphere of Earth during a severe solar storm when the planet is bombarded by intense energetic radiation.
The energy scales there are astronomical.
If the physics textbooks were wrong about what happens in a quiet room with a laser, could nature have been performing this exact type of forbidden light mixing all along? Could transient ultraviolet signals be flashing in the atmosphere during thunderstorms, generated by the exact off-resonant three-wave mixing process these researchers just uncovered, entirely unseen because we were mathematically convinced it was impossible? It makes you wonder what other fundamental impossibilities are happening right over our heads, waiting for us to finally build the right tool to see them.
It's a humbling perspective. It reminds us that our mathematical models are just approximations, and the universe is always more complex and far more creative than the rules we write to describe it.
It absolutely is. Thank you for joining us on this deep dive into the gas phase. Keep questioning the established rules, keep looking for the loopholes in the textbooks, and we will see you next time.